You need to do it, Ryan. It looks like. Okay.
Okay. Thanks, Rich. And it's great to be here. I'm Ted Haberman from Metadata Game Changers, and I wanted to talk about earthquakes and moving plates in the cloud today. I wanted to start out by talking a little bit about the organizations that are involved in this project. One is the Incorporated Research Institutions for Seismology. It's a NSF-funded repository that's been around since the 80s. Started in the late 1980s as a mechanism for archiving, preserving, and sharing seismological data. It's global access to global seismology data from all over the world, obviously, because such global coverage is important. And you can see from their website here, they're also involved in a lot of other things, education, all kinds of derived products, educational services for K through 12, as well as general public, a great resource for seismology and understanding the Earth. The second is UNAVCO, a similar history, started essentially at the same time as IRIS as an NSF-supported mechanism for doing GPS work around the world. Back in the days, some of you may not be aware of this, but GPS instruments were things that fit in the back of pickup trucks rather than in your pocket. And NSF in the 80s procured a bunch of GPS instruments that then could be used around the world for various studies of plate motions primarily. And UNAVCO was the organization that managed those instruments for NSF investigators. Their purview has also expanded considerably in the last 30 years, including participating in things like open topography. They also support a lot of educational output, educational efforts, and they happen to be located in Boulder. IRIS is located in Washington, and the Data Management Center is in Washington State. Several years ago, NSF, UNAVCO, and IRIS announced that they're joining forces. This really reflects the merger in the frequency space of fast things that are earthquakes and slow things that are plate motions, typically, except for during earthquakes, and that frequency band between slow and fast is really being filled in, and people are doing a lot of the same kinds of measurements on these two kinds of data. So in several years, UNAVCO and IRIS, also known as SAGE and GAGE in this context for seismological something and geodetic something, will be joining forces. And as part of that, they're also trying to figure out how to migrate their data centers from Seattle and Boulder into the cloud. And I've been working with them on that. So this is a picture that came out of one of the groups that's working on sort of archive processes for this combined archive. I just wanted to show it here, not to go through the details, obviously, but just to mention that, or to describe there's a lot of stuff going on in these archives. There's a lot of real-time data coming in. Both organizations are now involved in various earthquake warning systems. And those earthquake warning systems are for warning people during earthquakes. So if an earthquake's happening on the San Andreas Fault, say in California, it's a long rupture. It takes some time if it's a big earthquake, and they want to make warnings during at the beginning of the occurrence of that earthquake that it looks like something big is happening. So the real-time aspects of of data collection and also machine learning to try and recognize earthquakes early in their generation is going on. Lots of different products. We're thinking about Kafka as a mechanism for connecting to thousands of sensors in real time, and pooling some kind of data lake where real-time data is stored and when it's ready, migrated into the cloud, and being available in a lot of different ways. So it's a big task, and of course, as Rich mentioned earlier, I'm interested in the metadata as well as the data and pulling these things together. So it's a big and exciting project. The goal is to define a framework for handling a variety of data types in a cloud-native environment, and also in a standalone computer. And in this group, I don't have to mention that cloud-native environments and standalone computers are different. We want to think about both of these. And of course, this also includes things like analysis-ready data and access to data in the cloud by machine learning and other analytics. All these things are involved. We want to try to include in this framework all of the anticipated common cloud platform data types. So this includes the global navigation satellite system. Many of us in the US are familiar with GPS. It's been around for a long time. Now there are a number of other global navigation satellite systems owned and operated by other countries. So those are all included in GNSS. Also seismological data. DAS is a new kind of ground motion data collected by optical fibers that are, essentially thousands of sensors arranged in interesting geometries. Imaging, things like SAR, synthetic aperture radar, and also magnetotelluric data measuring currents in the earth, and we hope to provide a pattern to follow for future data types. One of the important ways that I've been attending these Pangeo meetings for a while and understand that access to data in the cloud is a different thing. An interesting paper came out a little while ago that has about 1.2 million earthquake and noise signals. It's a data set designed for machine learning. These are actually 1.2 million data sets. None of them are chunked. So there's actually 1.2 million separate items in there. And just as a test, I read 100 of them and computed means first on the disk, and doing this with H5Py. Standard HDF library for Python took 0.321 seconds. I moved the data to the cloud and did the same thing, and it took 25.7 seconds. So this is not this involves 100 reads of data and many associated reads of metadata associated with those data sets. So this isn't a surprise. Of course, this group knows that working with people that have been working in disks and on-prem repositories for a long time, it takes a while to help them understand what we're getting into when we move to the cloud. There's been a lot of discussion in this group about what I call structural metadata, which is offsets and sizes to data, either in the single object case, the offsets are 0. But I'm also interested in the work that Rich and Martin and Alex and others have done with XArray and HDF. So I used Reference-Maker, but instead of writing to JSON, I wrote to a SQLite database. Remember that this has 1.2 million data sets in it, and writing a JSON file with 1.2 million different data sets described, it turns out it's sort of a large one. But so most of the time, this shows that just seeking and reading just the data takes about 8% of the time, and reading the metadata takes 92% of the time. And in the cloud, the situation is similar. In this case, 3.14 seconds for seeking and reading just the data from the S3 object. So overall, we have a range in the time to read the data, and that this includes throughput and latency, varies by a factor of 1,000. So I don't have to tell this group that we're trying to figure out how to be on the left-hand side of this picture rather than the right-hand side. And obviously DASC and other parallel access mechanisms are going to be important in that. And that's something that we haven't started to test yet, but certainly plan to. Another problem is data organization. A lot of talks about that in this group. There is a format called ASDF, which is an HDF format developed by some people in Germany and at Princeton, maybe a decade ago or so. In this case, one day of data for 3 channels has 768 chunks per data set. There's 4,500 or so samples in those chunks. And so for a day, you need to read 768 chunks times 3 if you're interested in multiple channels. And those chunk sizes are pretty small. The data is compressed, so they're not all the same, but they're around 5K. One of the things I've learned from Pangeo is that's well, obviously 768 reads is going to be a problem. And we need to think about bigger chunk sizes. So if we take these daily files and combine 3 channels, 7 days, something like 84 megabytes as a weekly file. So we're testing different chunk sizes and access patterns. In many cases, people are accessing a small number of minutes of data. In this case, a seismic signal at a particular station. Pretty much the earthquake part of the signal is sort of in the order of tens of minutes. So that's an important sort of use case. But also, as I mentioned, seismic noise. People are now also accessing complete seismic signals and cross-correlating noise across stations to use the whole signal in addition to just the exciting, fast-moving part associated with the earthquakes. Obviously, I said this is too many and too small, and maybe this 100 megabyte number bounces around a little bit for a preferred size. So we might be able to get there with weekly kinds of files. So the proposals, we're now thinking about writing the data in HDF5 with the metadata essential for self-description. And this is really archival metadata read during ingest, not during the data access workflows. So, we're using the ideas that were developed in the reference maker work to then extract locations of data from these HDF files and accessing them, as I showed, just without using the HDF library, and also possibly with XArray and other kinds of access mechanisms that can go after data in some place. Data types, no surprise, simple data types supported by NumPy. One of the things we've discovered is that variable length strings are a problem in HDF. We know that from the reference maker work because variable length strings are really spread throughout the file. So fixed length strings can be contiguous and accessed using XArray and things like that. The compression technique, no surprise, anything supported by numcodecs and HDF5. A lot of great options in those groups. Chunks, index blobs of contiguous data. They're read at once so that they can be decompressed. And H5 Coro and other people are looking at chunks that are stored contiguously in objects or in files so we can read multiple chunks in one read. And of course, we know the offsets and the sizes of those so we can find contiguous chunks and we can write them contiguously. The data model, again, XArray with netcdf4 with coordinates. It turned out that many of the groups that have been working on developing formats for these kinds of data have already agreed on XArray. And so that was a great thing to say, well, good job, guys. We're following in your footsteps and also obviously the footsteps of many of the people involved in Pangeo. So metadata is important in the object store. Archival metadata sort of required for self-description. and then a database with discovery metadata of various kinds, that structural metadata for offsets and sizes, and then the scientific metadata that's also needed to understand and trust the data, instrument responses, provenance, software, et cetera, and then connections to people and organizations and papers. The important thing here is that the metadata that's in these in the objects is used during ingest or extracted during ingest, not typically used in regular workflows. So it's more like the reference maker approach that reads data from files rather than metadata and data. I have some questions for Pangeo. I mentioned that we have a lot of objects, multiple millions of files with potentially some number of chunks in those files. And so I'm interested in this thing that I tried of storing the XArray chunk metadata in a database. I know that there is a database backend available for XArray, and it seems, as I understand it from reading the documentation, it's mostly a key value pair. So you basically access some blob of stuff in the database using a key like you would a path to an object. I'm interested in actually being able to read with the XArray interface metadata from a database. Both of these organizations, UNAVCO and IRIS, have large relational databases that they use for discovery and data quality and availability, and that we'd like to be able to connect XArray into those. I have 3 questions here. I'll just put them all down. XArray says we can customize how XArray writes .cdf files on disk by providing different encodings for each data set variable. And my question is that also true for coordinate variables? I know that it could be true in HDF5. I'm not sure about XArray, but a lot of these data sets have uniform time spacing. Most of them have uniform time spacing. So you can compress that sort of away to nothing with the delta or the delta compression. And so we'd like to have coordinates that are compressed with delta and data that's compressed with some mechanism more appropriate for floats. That's the question there. And then chunk sizes, there seems to be this consensus that 100 plus or minus 50 megabytes is right. And I'd love to have some data that supports that consensus. And so maybe you guys can fill me in on some of these things, or others can educate me. So, the caveats were pretty conceptual right now in these proposals, and we're starting to use QHub and other things in the Amazon and Google clouds for testing. The takeaways, these things are things that this group knows pretty well. High latency, minimize reads, metadata in a database, read big pieces. XArray, we know, is a flexible and broad application and possible to extend. And it's a well-known open source tools and library. So that's the end. Maybe there's one more thing. Nope.